Every physical product around us, from the desk you sit at to the boda boda on the street, started as a simple drawing. Making processes is the systematic method of taking that technical drawing off the page and turning it into a functional physical object. Think of a practical repair, like making a mild steel angle bracket to fix a broken Ugandan school desk. To build that bracket reliably, follow a process plan with 5 stages: preparation, conversion, joining, finishing, and quality control. But first, establish a safe environment. Put on personal protective equipment, specifically goggles, aprons, boots, and gloves. Safety sits at the absolute center. Combining this strict step-by-step plan with absolute adherence to safety protocols is what separates chaotic tinkering from repeatable, professional engineering. Let's start the preparation stage for our mild steel bracket. The very first move is establishing a datum surface. This is a single, perfectly flat, square edge that serves as the reference point for every measurement that follows. This split screen shows why a datum is necessary. If you measure from an uneven edge on the left, your projected lines diverge, and the geometry warps. On the right, measuring from a perfectly flat datum guarantees straight, parallel lines. Once you have that flat edge, you need to mark it. Metalworkers use a high-precision metal scriber instead of a standard pencil. A pencil line is thick and rubs off easily, leaving a margin of error of over a millimeter. A scriber physically scratches a razor-thin groove into the steel, keeping your error under half a millimeter. Nailing this geometric accuracy at step 1 dictates the success of the final product. A tiny measurement error here multiplies with every cut and bend you make later. Moving into the conversion phase, we need to drill 2 8mm holes into our bracket. But if you press a spinning drill bit directly onto smooth, flat steel, the bit will walk or slip across the surface. This cross-section shows the mechanical solution. Before drilling, you strike a steel tool called a dot punch with a hammer. This physically displaces the metal to create a small V-shaped divot on your center mark. When the drill lowers, the tip of the bit locks directly into that divot, keeping it exactly centered. Imagine you're in an exam and you realize your punch mark is 2 millimeters off center. What do? Do you try to wobble the spinning drill bit to force the hole over, or do you stop, redraw your lines, and repunch? You always redraw and repunch. Trying to wobble a spinning drill bit destroys the dimensional accuracy of the hole. Worse, applying sideways pressure to a hardened drill bit can cause it to shatter, creating a severe physical hazard. In machining, attempting to force a correction mid-process is dangerous. True engineering requires stopping and applying a clean procedural reset. Next, we need to bend our 3mm steel strip 90 degrees. If you try to force metal this thick to bend at room temperature, you run into a serious structural problem. This microscopic view shows what happens during cold working. As the metal bends, the internal grain structure is forced to distort, slide, and lock up. This builds up internal stress, a process called work hardening. The metal becomes harder, but it also becomes brittle, leading to microcracks at the bend line. The alternative is hot working. By heating the metal to a cherry red state, above its recrystallization temperature, the material becomes highly malleable. Now, when you bend it, the crushed grains instantly heal and reform into new, stress-free structures. This table compares the 2 methods. Hot working requires low force and prevents cracking, but leaves a scaly, rough surface. Cold working requires high force and risks brittleness, but yields excellent surface finishes and high dimensional accuracy. Consider a boda boda engine gear. Engineers hot forge it first to get a tough basic shape, then cold finish it to achieve the exact precision needed to spin smoothly. Shaping material is a calculated trade-off between the internal molecular strength required and the external precision needed. Once the bracket is shaped and drilled, we move to the finishing stage. Cutting and drilling metal always leaves behind burrs, sharp, ragged edges of excess material. You must use a file to remove these burrs immediately so the piece is safe to handle. This diagram shows the quality control phase. We measure the final bracket against the original design specifications. A tri-square checks that the 90-degree angle is exact, and we measure the hole alignment to ensure it falls strictly within an acceptable tolerance window, like plus or minus 0.5 millimeters. If you need to make 100 of these brackets exactly the same way, you rely on specialized tools. A fixture holds your raw materials securely in the correct position, while a jig physically guides your drill bit to the precise hole locations every single time. This guarantees efficiency and accuracy in mass production. To dive deeper into these manufacturing principles, review the full syllabus modules and class materials available on the Yaka network. Mastering the making process takes you from simply using hand tools to thinking like an engineer. By applying sequential planning, understanding metallurgy, and demanding rigorous quality control, you build reliable realities.